Let me now disentangle communication from information transfer from causal influences. This is the Berlin TV tower. Charlie is in control of sending, transmitting the radio waves. Now, this is a classical model to distinguish the semantics of the terminology. There's no quantum in here now. This is about distinguishing differences between information correlation, messages, and signals. So Charlie is in control of a Morse code feed. He needs help, so he can send an SOS to Alice and to Bob. If he can control the event transmission, and so SOS goes out to Alice with the radio, she has a receiver, and to Bob. And this would be direct cause information transfer, both. So there's a direct cause, radio waves going here, receiver, and it would be common cause information transfer for Bob and Alice. So of course, Alice and Bob, they're not communicating, but they are in a common cause relationship with Charlie. So in this case, you have perfect informational correlations that do communicate a message, SOS. And this is what we call a Shannon signal. It's very helpful to make that distinction. You know, when you say about non-signaling theorem, what is forbidden by the non-signaling theorem? What is forbidden by it is the Shannon signaling part. The next step is not forbidden. And that confuses a lot of people, and that's why we've written that paper. Now, what if Charlie still sends out his dots and dashes, but he's not in control of what he's going to send? So a random event generator is generating that sequence. So he's sending out that sequence. You again have perfect informational correlations, just like in an EPR-type experiment. But in this case, you have perfect information correlations, and there was no message communicated. So in this case, you have transmission of non-Shannon signals, just detector clicks, fully correlated, that are not communicating any message. So this is an introduction of terminology. You know, when somebody says, you know, how do you interpret the non-signaling theorem? Which signal, which type of signal are you not allowed to transmit? And so based on that, on introduction of this terminology, you can very nicely define the non-signaling theorem that Bell used in 1964, and we call that the axiomatic non-signaling theorem. And then in 1976, he changed to a different kind of non-signaling theorem, and we call that effective non-signaling, in contrast to axiomatic non-signaling. And that's the one that the realists must use. And in Bohmian theory, you must use this principle. And the difference, of course, is that axiomatic non-signaling prohibits the propagation of both Shannon signals and non-Shannon signals. Whereas effective non-signaling, and Bell has realized that, only prohibits the transfer of Shannon signals, but it does allow the unlimited transmission of non-Shannon signals. So that's a terminology that's helpful to people, and we want to share that with you here. Now, now you can build out of this. Non-locality and non-axiomatic non-signaling are incompatible. In 1964, you're not allowed to have any ontic influences, no transmission of information, and that's why we have a no-influence theorem in Bell 1964. It's not a non-signaling theorem, it's actually a no-causal influence theorem. And in causal network analysis, you know, that Matt Leifer has shown us and others, when we say, okay, we have violation of parameter independence in the Bohmian model, that was the first graph I think Matt showed us, and if you then say, oh, non-signaling is disallowed, what is really said there, no causal influences are allowed. However, and this means, here non-signaling means violation of causality. So I hear very often in orthodox interpretations, they say, oh, non-signaling simply means violation of causality. That's not what Bell meant in 1976. And this comes from the following, by the way. This is our first figure in the paper. If you have axiomatic non-signaling, then how do you know the axiomatic non-signaling assumption is true? It is true only if you assume intrinsic randomness, objective chance in the universe. How do you know that your experiments, like Emily told us, that you actually have objective chance, intrinsic randomness in the universe? It's because you need to assume in the experiments that the experimenter has free choice to make his settings, to contrast the superdeterminist view. But that depends, that that model really has the fallacy of circular reasoning, because the use of non-signaling as a valid argument against determinism depends on the independent validity of these two assumptions. But these two assumptions are completely circular, and I'm going to come back to that in the end. And I call that super indeterminism when I have time. Now, the effective non-signaling theorem by Bell 76 is fully compatible with non-locality. Here, non-signaling means prohibition of communication, prohibition of message transfer, prohibition of controlling an event over there at will. That's what signaling really means in this context. So, all I want to do, how much time do I have left?
7 minutes, 7.5 minutes.
Okay. Now, in a retrocausal model, you have the same problem. If you imagine you have a causal influence coming from the future to the past, and I think, Ken, you mentioned closed time-like curve approaches. And if you think about all the paradoxes that can, Tolman's grandfather paradox, you know, somebody traveling from the future into the past to kill his own grandfather, that is inconsistent with the existence of that person in the future, you have a paradox. The question then is, can you send? You're not allowed, of course, to send a message back from the future into the past to have your grandfather killed. That would create a causal paradox. But can one send back random bits of information? Can you have retro signaling from the future and the past? Would that create a causal paradox? Yes or no? That's something to think about. So I want to introduce these two types of non-signaling theorems. So here, in the first case, if a retrocausal model applies axiomatic non-signaling, the 64-Bell theorem, here non-signaling means no retrocausation. You can't have any causal influences in the axiomatic case. So the retrocausal models do need an effective non-signaling theorem, because in this case they are compatible, because all that's prohibited by an effective non-signaling principle is the prohibition of retro-signaling or retro-communication from the future to the past. Finally, and I think Matt Leifer would ask this question, because in his talk was not, the problem was not non-locality as such, but the fine-tuning problem. Why can't we use superluminal signals or spooky action at a distance for signaling? The puzzle then does not become the incompatibility or incompatibility. The puzzle becomes why it cannot be used, why we cannot control it. And there's answers. It could be an emergent universe. It could just be a fact of emergence. Then in that case, emergent quantum mechanics would be a fine-tuned quantum mechanics. And we have to live with this. This was one option Matt talked about. But I suggest an explanation for this. And if in orthodox quantum theory, if you now include the agent in the universe, you have an agent-universe relationship. And in the orthodox approach, and also in the axiomatic approach of Bell 1964, the source of the unpredictability is intrinsic randomness, objective chance. And you might call this universal indeterminism. Agent and physical universe are subject to the same fundamental indeterminism. The in-principle unpredictability of physical events is a function of intrinsic randomness. However, in this case, and this is shown in this paper, indeterminism neither rejects nor affirms the reality of free will or free choice as a consequence of super indeterminism. In the other case, so where does Bohm's quantum theory, where in a deterministic universe do you get your unpredictability from? You get it from intrinsic complexity. And we've heard Tim Palmer's talk. That's where he was heading with his proposal. And in that model, you have, yes, you do have universal determinism. Agents and universe are subject to the same fundamental determinism. The in-principle unpredictability of events is a function here of the intrinsic complexity. Note that determinism need not be identified with predeterminism as a consequence of universal uncomputability. That's what I want to say. And what do I mean by that? I come full circle back to my opening presentation when I briefly talked about what is emergence. And there's a connection between intrinsic complexity and universal uncomputability. In principle, unpredictability of individual events is possible in emergence if they're based on self-referential recursive processes. You can imagine like a halting problem in computational theory or something like this. So all self-referential, self-feeding states would require an infinite amount of computational resources to actually predict the microscopic next event. You can make probabilistic predictions, but you cannot on a case-by-case. It would be like saying, I could predict where the raindrop falls 200 years from now in the hurricane over New York in a deterministic universe. And I think there might be a limit to that. That is an operational constraint. Mathematical physicists might not like that because you'd like your mathematics to be close to reality. But maybe in quantum mechanics, we are hitting a brick wall. And the brick wall is what agents can and can't do. And that might, and in Bohmian theory and in effective non-signaling theories, that constraint is part of the quantum interpretation and the argument that you require to distinguish between the success of different interpretations. So you can have determinism without predeterminism in these cases. And an example is, of course, deterministic chaos. So thank you very much.